So this is a video on enzyme kinematics. So let's say that you have a general, like the most kind of general enzymatic reaction you can have. We have enzyme plus a substrate form an enzyme substrate complex, which then results in a product and the free enzyme being released again. So with this one, maybe we can call the forward rate K1, the backwards rate here K to the negative 1, and this rate K2. And there's different ways that we can write the kinetics of this. So the two main ones are called quasi-steady state assumption, and then the second one is fast equilibrium. The former will have more math, but will be a more accurate representation of the kinetics of this enzymatic reaction. Whereas the fast equilibrium, it's more of simplified. It has easier math and you can solve it more easily, and it ends up being a simplified result of the quasi-steady state assumption. So the quasi-steady state assumption, it has more detail to it. It ends up getting reduced into the fast equilibrium assumption if you make more assumptions, like, oh, maybe if one of the products is an excess or something. I'll show you the math though. It becomes really easy. So what you can do is define a general reaction rate as like this, and usually, yeah, we want to do that for the product. So we can say that this is just dp over dt, and usually we write it in terms of the stoichiometric coefficient, like you do it like that, so it ends up just being the same thing, because if this was different, then that'd be different. And it ends up just being K2ES from the conservation. So what you can do is, let's say we want to do the quasi-steady state assumption. To do that, you assume that the intermediate has a rate of change equal to 0. And then what we can do is we write the conservation equation for that, so it ends up being, let's see, the formation of it minus that left reaction, and then minus this one, because that's going to be reducing the concentration of it as well. And that equals to 0. Okay, so we have that. And what we can also realize that there's enzyme conservation. So E0 is like the initial amount of enzyme you put into the system, and you know that if you put only so much in the system, this will be equal to anything with E in it, which includes the free enzyme and also the enzyme substrate complex. In this particular case, it's very simple, so it's just E plus ES. And you see from this equation above that equals 0, we can isolate in terms of ES. See, when we end up finishing the equation, it should only be in terms of the substrate and the initial enzyme concentration, which is a constant here. It's only going to be a function of S. Like, we shouldn't have free enzyme or ES into the equation by the end of this. So for this, what we can do is factor of the ES and move it to the other side. That will be K1 ES. So ES equals, and you just have to do the mathematics. It ends up being a lot of algebra in the end. So E0 equals to And then just factor out the E as well. Makes it easier, plus... Hope I'm not doing this too quickly, but you can see it's not too bad in this case because it's just the most basic kind of enzyme substrate reaction we can have. It can be a lot more complicated than this. And you'll get E in terms of only S and E naught. There we go. Now if we go back up, what was the product formation? It's just K2ES. Let's write that down again. And then, you remember what ES was? It's this piece. Okay, and then we substitute E into this equation, and we plug it all back in. And then we have the E naught part, so and we can actually simplify this. We can move this into that. See, the thing is, we want, what do we want? We want, and this is just the reaction rate. We want to get this form. We might not necessarily be able to get it, but if we can get it, this is what we want. It's a Michaelis Menton kinetics, where the numerator, this Vm constant, is the maximum velocity of the reaction, and this other one is the Michaelis constant, which is just the concentration value when the reaction velocity is half of its Vm value, which is like half of its maximum reaction rate. By definition, we want to see if we can get that form. Is it possible? We have, before we actually, we could just say that this is Vm, but let's actually just try to simplify it before we do that. See, you just multiply that inwards and this will cancel out. And what do? We need to divide by k to the negative 1. So what are we doing exactly? Well, it's really just like doing it by 1. See, a lot of people get confused by this because they're not comfortable dealing with the arithmetic in the fractions. But what you're really just doing is you're multiplying by just 1. But you just have to make sure you do this for like both the numerator and the denominator. You see what I'm saying? And you'll get this. And oh wow, now it looks beautiful because now you know what you can do next. V equals VMS over Km plus S. And it looks good. So Vm equals, and it's just a bunch of constants. Remember that E naught is a constant as well. And there you go. So we solved the most general kind of enzymatic reaction using using the quasi-steady state assumption. So the thing is that if you actually make all of the differential equations, you'll get the perfect solution, and you can do that numerically using a program that can solve differential equations, but you can't get an analytic solution. By using the quasi-steady state assumption, we're assuming that the enzyme substrate complex intermediate, it is used up as soon as it's formed, such that you remember what it was. We did dES over dt equals 0, which means that like it's getting used up as soon as it's like being made, like such that like it's like there's nothing at any time. And yeah, using this particular assumption, you end up with a very general kind of form with these representations of the maximum velocity and the Michaelis constant. And you'll see that if you actually did, as I said in the beginning of the video, if you use a different kind of assumption like fast equilibrium assumption instead, you would still get Michaelis Menton kinetics. But the thing is, you'd end up with different values for Vm and Km. It will end up being a less generalized form as what we have here. You'll see that you actually have less constants because the assumption, it's less generalized. But there you go. This is how you do the most basic kind of enzymatic kinetics reaction you have. So you just use these steps. If you ever asked on this on an exam, and you just work from there, it's not so bad. Yeah, as I said in the beginning, you can have a lot more intermediates being formed. You can have maybe competitive inhibition where there's like an inhibitor chemical that ends up also binding with the enzyme. You have a whole bunch of different things. You could have different products being made, and you'll see that if you do that, mathematics will become much more complicated. But you just have to work through it slowly, and depending on what you're being asked, if you're being asked to solve to make the product formation rate, and you're told you can use any assumption you want, you'd probably want to actually use fast equilibrium assumption and not quasi-steady state, because the quasi-steady state has more mathematics behind it. I had a prof who would ask this, and he said, oh, you can use whatever you want. I ended up using the quasi-steady state assumption, and the problem is that yeah, it's in real life it's good to do because it's more generalized. But on an exam, if the prof is going to give you the same marks for doing either the quasi-steady state or fast equilibrium, you want to use fast equilibrium assumption because it's more fast to do the math. And the generalized form, it's not so bad, but it really depends on what application you're doing this for. And there you go. So in the next video, I'll probably make one detailing the fast equilibrium assumption instead, and we'll see what we get.